Okay, so in the last video we talked about the Compton effect, and in it I said think of a photon or a quantum of energy as a little packet of energy that doesn't have any mass, that moves like a wave. Okay, so it's like a little particle with no mass, it's moving in a wave. And that was at the Compton effect was like 1922. So in 1924, there was a physicist, a French physicist. His name was Louis de Broglie, Broglie. And so he said, if light can be a wave with this little packet of energy that looks like a particle that's moving as a wave. So if it can have both wave and particle characteristics, maybe all matter that is in motion does. So his theory is that all matter in motion could have both wave and particle characteristics, so that all matter in motion, like light, could have a dual nature. And that would go for electrons all the way up to like a football or a baseball. Okay, so he's saying any matter that's in motion, so obviously not us that are standing still, but if we throw an object, then perhaps it's like this little packet of light. Maybe it's moving in wave form. So he set about to find what's known as the matter wavelength. So it's often referred to as the matter wavelength or as de Broglie's wavelength. Okay, because it's named after him. So de Broglie's wavelength is the other, whoops, there's an I in there. De Broglie's wavelength is the other name for it. And what he does to find it is really quite simple. Remember, we know that we defined the momentum of light, of a photon, to be P equals HF. Let me see if I can straighten my writing out here. But we know that P is equal to mv. So then, for a matter, so then that would mean mv was equal to h over lambda. I said hf up there, but I really wrote lambda because I meant lambda. So if we want to find the matter wavelength, it will just be lambda equals h over mv. So this is our equation for the wavelength of a particle. Matter wavelength in a particle that's in motion. Now, so we could do this. Let's do an example. And we could do it for an electron. And let's say the electron is moving at a speed of 2 times 10 to the 6 meters per second. And we could also do it for a baseball. And let's say it's moving at a speed of 25 meters per second. The mass of an electron, of course, is 9.109 times 10 to the negative 31. And the mass of a baseball is probably about 0.4 of a kilogram. Okay, so we're going to find the matter wavelength for both of these. So lambda equals h over mv, 6.626 to the negative 34 kilograms. The mass of an electron, 9.109 to the negative 31 kilograms, and its speed is 2 times 10 to the 6 meters per second. And when we do the math, we get 3.6371 times 10 to the negative 10 meters. Okay? And then if we do it for a baseball, I'll come back and talk about that answer in a second. Let's just do it for the baseball first. So h over mv, 6.626 to the negative 34. I wrote kilograms, but it's joule seconds. Joule seconds over, we said 0.4 of a kilogram, and you're throwing at 25 meters per second, 90 kilometers per hour, so that's a pretty good speed. And we get a lambda that is 6.626 times 10 to the negative 35 meters. Okay. All right. So this would be the wavelength that the electron is moving with. This is the wavelength that the baseball would be moving with. Now, when I said this, when I said like Broglie's theory was that not only can light have a dual nature, but that all matter in motion can, we accept that he's right, okay? And we actually have some proof of it. This wavelength of the electron we can measure. We can measure times 10 to the negative 10th. We can see this. So we can see that an electron is actually moving in wave form. So we know de Broglie's correct. You might say, well, if that's true, then how come when I throw a baseball or I throw a football or I throw a rugby ball or a basketball, how come I can't see the waveform? Well, the reason is in the math. Because a baseball, a football, a rugby ball, any ball weighs an awful lot more than an electron, and there's no way it can move as quickly. Look at it, the size of its wavelength, times 10 to the negative 35. It's way too tiny for us to be able to measure, to be able to notice. Okay, so we believe his theory is true, and we say the reason that we cannot, see this for larger objects is because it's too tiny. But we can see it for the subatomic objects, and that's why we know or we feel that de Broglie is correct. Okay, so that's one piece of today. The second piece is, because of this, then we can link de Broglie's wavelength in with the photoelectric effect. So now all those questions that you were doing, where it was telling you the threshold frequency and the wavelength of the light coming in, well, now we could also tell you about de Broglie's wavelength for the electron. So let's just try a little example here. Oops. And here's the example. So its light strikes a photoemissive surface whose threshold wavelength is 720 meters. So the threshold wavelength, lambda O, is 720, and that was nanometers, even though I said meters. If the electrons emitted have a wavelength of 2.09 nanometers, so that's the wavelength of the electron, 2.09. That's de Broglie's wavelength, nanometers. What color was the incident light? Okay, so from de Broglie's wavelength, lambda equals h over mv, we can get the speed of the electron. So h over m lambda, 6.626 to the negative 34 joules seconds, divided by 9.109 to the negative 31 kilograms, and the lambda is 2.09 to the negative 9 meters. So we get the speed of the electron, and it's 3.48044 times 10 to the 5th meters per second. And why is that helpful? Because then we can get the EK max of the electron, because we know that's equal to 1/2 mv squared. So EK max is equal to 1/2 the 9.109 times 10 to the negative 31 kilograms times this 3.48044 to the 5th meters per second. Don't forget to square it. And so we can find the EK max of the electrons, that the energy with which the electrons come off the metal, 5.517084 to the negative 20 joules. So that's my EK max. Okay, so that's with this wavelength. Now with this wavelength, it was the threshold wavelength of the metal. So from this, we can find FO it's equal to C over lambda O. And then once we have FO, we can get our WO.